All right, so here's what we want to go over, guys. Okay, quick review of some naming stuff real fast, and then some solubility terminology, and then we'll talk about question 11 because, like I said, I forgot to teach you that the other day. Okay, which good thing we did this quiz, or I probably would have completely forgotten about it. All right. So number one, we've got magnesium with hydroxide, so it's an ionic compound. Magnesium hydroxide. Okay, again, they all have to be lowercase. Okay, number two, we've got silicone and nitrogen, molecular compound. There are two silicones, so disilicone. Okay, trinitride. And number three, we've got cobalt with oxygen. Cobalt is a multivalent metal, so we have to figure out which charge it has. Okay, this oxygen is -2. That gives us 6 negatives. We have to get 6 positives with 2 cobalts. That means each cobalt is +3. So this is cobalt 1, 2, 3 oxide. Any questions on the first three? All right. Number 4, we got copper 1 sulfate. What's the 1 tell us? The charge. Okay, so in the swap and drop, copper is a +1. Sulfate, SO4, is a -2. So we have Cu2SO4. Okay, for number 5, we've got oxygen monosulfide. The prefix mono means how many? 1. OS. And we've got hydrogen phosphate. So hydrogen's always +1. Phosphate is PO4, and it is 3-. When we swap and drop, that leaves us with H3PO4. There is a polyatomic ion that is hydrogen phosphate, but it doesn't look like that. Right? Okay, if I give you the name of a compound, you have to do the compound naming. Follow me there? Okay. Now, that compound, as a tip for some of you, because I had a few questions with identifying some of the compounds yesterday from the lab, what properties is that compound going to have off the top of your head? Right. Hydrogen is acting as a metal here. Anything where hydrogen is acting as a metal is acidic. Okay, so this is an ionic compound that is going to be acidic. So you're going to have, a white crystalline solid probably, okay, that dissolves easily in water, probably has a conductivity of 10, and has a pH of 1. Okay, something like that. So those are the things, that's kind of the thought process you need to go through when you're figuring out which substance is which on your lab report. Okay, that's due Monday. All right, number 7, a solid produced in a reaction that will not dissolve is a precipitate. Spelling doesn't count on that one, but just so you know, precipitate is not correct. I'll let it go today, but precipitate is the correct word. I'll let it go, though. You know what they meant if it says precipitate. Okay, number 8, any substance that will dissolve in another substance is a solute. A substance that is dissolving, that will dissolve another substance. Sorry, I got that mixed up. Sorry, this is solvent that dissolves something else. The next one, the substance that is dissolving is solute. Sorry, guys. I'm only half done my coffee, okay? I'm only half awake. All right, number 10, when water forms hydrogen bonds with itself, we call this process cohesion. Okay, so let's say for right now, give them a mark out of 10. Why do I have that as out of 13? That doesn't make any sense. It should be out of 14. Well, yours is out of 10 because we didn't do the last question. So, okay. All right. Give them a mark out of 10. Let them see it. Okay. Put it in the box, and then we'll go over how to use your solubility chart. All right, if you can please take out your periodic table, flip to the back side of it, you will see this chart in the top left-hand corner. Solubility of some common ionic compounds in water at 298.15 degrees Kelvin. Okay, basically it's room temperature. All right. So here's how this chart works. Okay, this chart will allow you to figure out what compounds essentially in a reaction could form or have formed precipitates. And that's going to be important now that we're moving on to reactions today. Right? So sometimes you'll have a reaction where two things react and a precipitate gets formed. What you have to do is figure out, okay, what's in the precipitate and what's left dissolved in the remaining fluid that I have after this reaction has occurred. It's important to know that in case you're collecting one or the other for a use in another experiment. Okay, so here's how it works. You look up the ion that it's attached to, usually the negatively charged or non-metal, okay, ion up top here. And then you look in the rows below. So let's say that the compound I'm looking at is sodium fluoride. All right, as an example. So I look up fluoride. It's right here. Fluoride is soluble with so many things that they actually just write most, okay, in this first row for it. All right? Anytime you see most, what you have to do is actually look down below in the row that tells you what it's not soluble with and see if what it's with is there or not. All right? So in this case, I look down below. I was looking up sodium fluoride. I don't see sodium in the list of things that fluoride is not soluble with. So sodium fluoride is soluble in water. All right. If we were dealing with magnesium fluoride, that would be insoluble, right? Okay, that would be a precipitate if it was formed in a reaction. Everybody follow me there? It's pretty easy to use. Okay, you look up the ion on top, you check and see if it's in the first row, it's soluble. If it's in the second row, it's not. Pretty easy, right? Okay, so let's go back and tell me which of those are soluble and which are not. All right, so let's quickly have a look at these. So we've got magnesium nitrate is our first one. Okay, so we look on our chart. Nitrate is right here. Okay, and it says that it is soluble with most things except for these gigantic polyatomic ions that we're not dealing with. So is that one soluble? Yeah, in fact, nitrate's soluble with essentially everything. Right? Nitrates are highly soluble in water, which is why they're used in fertilizer. They dissolve easily and soak into the soil. Okay, and be absorbed by plants. All right, our next one. Mercury sulfate. Right, and this is actually mercury. Which mercury is this? This is the mercury 2, and that actually makes a difference. All right. So if we look at our chart here, sulfate soluble with most things, but not calcium, strontium, barium, or mercury 2+. So that is insoluble. Oh, yeah, I think that's actually a typo. It's just 2+. Okay, yeah. All right, next one here. Okay, we got sodium phosphate. Okay, so we look up phosphate. PO4 is right here. Okay. Soluble or not? Soluble. Okay. And lastly, lithium fluoride. Oh, I think we looked at that one. So fluoride, soluble. Nope, not with lithium. Okay, so that one is insoluble. Pretty easy? Okay, so that's all you have to do with that. Alrighty, so we are going to move on to reactions now, guys. If you have your notes print out there, you are looking at lesson 12. Okay, now, see, I would have remembered once I got to this slide. Practice, solubility chart. I'll give you a couple minutes. Soluble or not soluble beside these compounds. Please and thank you. Okay, so if we are looking at calcium sulfide here, okay, calcium, so we look up sulfide. Oh, come on. Okay, sulfide's way over here, right? For calcium is listed in the first row, so is this stuff soluble? Yes. Okay, sodium oxide. All right. I don't even have oxide up there. No, forget about that one. Can't even do that with this chart. What's that? Oh, so, okay, yeah. All right, we can do it that way then. Okay, so sodium is soluble with most things except for these, so sodium oxide is soluble. Usually you don't see positive ones in this, so I never looked. All right, potassium hydroxide. So hydroxide was way over on the other side here. Okay, and hydroxide is soluble with potassium right here. All right, so that one's soluble. Lead 2 chloride. Chloride is right here. And it is not soluble. Lead 2 plus is down in the second row. Okay, tin 4 fluoride must be soluble. Don't see tin 4, okay, in the non-soluble row. Copper 2 sulfide. Is that no? Is that sulfide or sulfate? Sulfide. Okay, so sulfide. Okay, not soluble. Right, don't see copper in the soluble row. Iron oxide, iron 3 oxide in this case. Okay. Yeah, won't be able to do that one because oxide's not on this chart. Don't worry, on a test I would never give you one you couldn't do with this chart. Okay, potassium fluoride must be soluble. Potassium's not listed there in the second row. Silver fluoride, also soluble. Silver not listed in the second row. Can't do number 10 because oxide's not on here. Okay, beryllium nitrate. Well, nitrate's up here, soluble with just about everything, so that one's good. And lithium nitride. I don't think nitrogen's up there either, is it? Okay, so, yeah, so you can't do that one either. Okay, sorry about that, guys. I got a new chart, and then I forgot to change my slide over to reflect the new chart. Okay. What we got to go over today, signs of a chemical change. That's review from Science 9. You know those already. Okay, we got to go over the 5 types of chemical reactions that we're going to deal with. Okay, in general, most reactions can be classified into those types. There are a few exceptions to that. All right, and then how to write them. How to write out a chemical reaction, okay, in formula form, in word form, and also how to balance it. Okay, the importance of balancing a chemical reaction is to make sure that you obey the law of conservation of matter. In a chemical reaction, can you create matter? Can you destroy it? No, all matter must continue to exist. Okay, so we have to make sure that in our reaction we don't suddenly have more of something on one side than the other. All right, so moving right along here. So a chemical change or chemical reaction has occurred if our final products are chemically different from our starting reactants. Terminology for you. Products are the things that are produced in a chemical reaction. Reactants are the things you start with. Okay, so in a typical chemical reaction, okay, you start out with, let's say, hydrogen chloride plus, can you guys see that at all, or maybe green would be better? Let's say these two things are reacting. Okay, when they react, they will produce those two things. Okay, that's a very basic chemical reaction. Okay, these are my reactants. And on the other side of the arrow are the products. Do I have the same amount of everything on both sides of the arrow? Yes. Okay, I've got 1 hydrogen and 1 hydroxide. And there's 1 of each over here. 1 sodium, 1 sodium, 1 chlorine, 1 chlorine. That equation is also balanced. State change can happen in a chemical reaction. It is a physical change, but usually you see a state change in a chemical reaction because something that was produced that's new is in a different state. Okay, like I might have had 2 things that were dissolved in water, and the result of the reaction is that one of them becomes a solid. Okay, well, I didn't change the state of my starting material. I produced something else that only exists as a solid. Yeah. All right, so odor change, typically a gas can be evolved in some reactions, okay, and so you smell it. Energy change, meaning it could get hotter or colder, as the case may be. All right, color change, obviously a very good sign that a chemical reaction has occurred. Okay, lots of things. Okay, lots of things can happen in a chemical reaction, but those are our basic signs that we're looking for. When we do our chemical reactions lab next week, okay, those are the things you're going to be looking for, signs of a reaction occurring. Questions so far? when you have a chemical reaction, can you get the starting materials back? No. Well, I mean, it's not impossible, but usually to make a reaction go the other way requires a lot of energy. Right? It isn't naturally going to go that way. Nature always seeks the most stable state. That's why reactions occur. Okay. All right, 5 types of chemical reactions, and these you absolutely 100% have to know. Because when we get to predicting the products of a chemical reaction, the only way to predict what products will be produced is to know what kind of reaction is going on. So you will have to be able to identify a reaction type from only the reactants. So you will only get 1/2 of the equation here to work with. Sorry guys, some spacing got messed up there. Okay, so in a synthesis reaction, 2 or more elements, usually elements, it could be a compound and an element, right, but most of the time it's going to be 2 elements, will react to form a single compound. Right? The key thing here is that 2 things react and form only 1 product, right, which is why it's usually 2 elements reacting. All right, so in our first example, we've got magnesium metal, so a solid, reacting with oxygen gas, okay, to produce magnesium oxide, right, which is kind of a black powdery material. Okay, what do the S and the G stand for? Solid and gas, okay. Sometimes you'll see AQ written beside. That means aqueous, dissolved in water. All right. L stands for liquid. Okay. Now, is this reaction here balanced? How many magnesium on this side? 2. How many over there? 2. Okay. How many oxygen over here? How many over here? 2. Okay, this 2 here applies to everything behind it. It's almost like there's brackets here, okay, and sorry, I keep using colors you can't see. Okay, it's almost like there's brackets here, and the 2 applies to everything behind. Okay, follow me on that one. So that's how we balance equations. We actually have to write in these big numbers in order to make it work. Okay. Now, this reaction here, I've got 2 potassium atoms reacting with a bromine molecule, okay, which is essentially 2 atoms of bromine, to produce potassium bromide. Is this balanced? Yeah, visually it's really nice because you can see all the atoms there. All right, in real life you can't do that, obviously. Okay, so in a synthesis reaction, 2 elements combine to form a single compound. Now, most of the time when you get a synthesis reaction, the compound produced is going to be ionic. Anybody know why? Is it possible for you to know, if it was a molecular compound, how many of each atom there would be in that compound? Because you don't swap and drop with molecular compounds, right? So if I told you nitrogen reacts with oxygen to produce something, there'd be no way for you to know which nitrogen-oxygen combination is actually being produced, right? So if I'm asking you to predict the products, it's going to be forming an ionic compound because that's the only way you could reliably do it. All right? Okay. Next one is the opposite of synthesis. Okay? Some things spontaneously decompose. All right? So a decomposition reaction, okay, is one in which we have a material, a single reactant, breaking down into its constituent parts. All right, so in this case, we have water in the presence of a strong electric current breaking down into hydrogen gas and oxygen gas. All right, so it breaks down into its 2 elements. Right? Is that reaction balanced? Okay, how many hydrogen over here? 4. Right? 2 times 2 gives us 4 hydrogens. How many over here? 4. Okay. How many oxygen here? 2. How many over here? 2. Okay? So that one is balanced. Another example, okay, nitrogen triiodide breaks down into nitrogen gas and iodine liquid. John? when water is written H2O, it's molecular. If I write water HOH, I'm making it behave as an ionic compound. Okay? In some reactions, you're going to want to write it as H2O, and in some reactions, you're going to want to write it as HOH. And as an example, if I had water reacting with something and one of my products had OH in it, it's way easier to follow where everything goes by writing water as HOH. Since it's split up into H and OH anyway, it's better to treat it like an ionic compound. Whereas if it splits into hydrogen and oxygen on the other side, then it's better to treat it this way. Yeah. All right, and then this one here, again, we've got it balanced. How many iodines here? 6. 6 over here, 2 nitrogens, 2 nitrogens. Okay, it's all balanced off. I wonder why I have that there. Okay. All right, combustion reactions. Okay, in a combustion reaction, something is burning. Burning is a reaction with what? The key ingredient in air. Oxygen. All right, so combustion reactions, more specifically they're called hydrocarbon combustion reactions, okay, are the reaction of something containing carbon and hydrogen, okay, with oxygen to produce always, okay, the products are always the same, carbon dioxide and water. Okay? Anytime you set fire to something, these are your products. John? Not always. Okay? Propane will often produce liquid. Now, if in your barbecue, where the barbecue itself gets very hot, the liquid is quickly vaporized. Okay? But on a really cold day, you often see like drops of water coming out of the exhaust pipe of vehicles. Water was produced as a gas, but it condensed as it went through the exhaust system and cooled down into a liquid and came out that way. All right, so in this reaction we have, okay, we have to check and see if it's balanced. How many carbons here? 6, okay. How many over here? 6, so that's okay. How many hydrogen here? 16. 2 times 8 is 16. 2 times 8, 16, so we're good there. How many oxygen on this side? 14. All right, 6 times 2 is how many? 12, plus 8 more is 20. Is that reaction properly balanced? It is not. Okay, what should I have there? Not 2. 10. Yeah. Okay. Now, here's the other problem, and I did this on purpose because I wanted to illustrate a couple things here. All right. 2, 10, 6, and 8 can all be divided by 2. Okay. The proper balancing for this is actually 1, 5, 3, 4. All right. Whenever you can reduce your balancing, you do so. Okay. So whenever you can reduce your balancing, you do so. Now, there's a couple of rules, special rules, when dealing with combustion reactions, and you're going to want to write this rule down. Okay, it's the balancing rule. Okay, for combustion reactions. We always balance the reaction alphabetically. It is the only reaction that you balance alphabetically. Okay? If you do not balance it alphabetically, you will balance it for a very long time, because oxygen will almost always throw you off. If you try and balance the oxygens first, you won't get the right numbers. And if you try and balance hydrogen, it won't work. Okay? So always balance it alphabetically. Carbon, hydrogen, oxygen. Okay. When you're balancing other types of reactions, you typically take whatever is in the largest number in the reaction already and start with it. Okay. Typically everything else falls into place then. Okay, let's look at another example of a combustion reaction here. Let's try this one. All right. This is the other. This has to do with the other balancing rule. I got 8 carbons here. So what do I need to put here? An 8, right. Okay, so now I have 8 carbons and 8 carbons. I've got 18 hydrogen on this side. What times 2 will give me 18? 9. Herein lies my problem. I am going to have an odd number of oxygens over here. Is there any whole number times 2 that will give me an odd number? No. Okay, so what you're going to find here is that you'll get like a decimal, a 0.5. Well, you can't put a 0.5 in there because you can't have half a molecule. Everybody follow me? So, what do you do to something that has a 0.5 in it to make it a whole number? Times it by 2. So take whatever you had, start there with a 2, and balance again. That only happens when carbon is present in even numbers. Okay? If you have carbon in an even number, start with a 2. That's the second balancing rule. Okay, so if we reset all of our numbers here, okay, now with a 2 up front, how many carbon are there? 16. All right, so I put a 16 here. Okay, and now I have 36 hydrogens. Okay, 18 times 2 is 36. Now I have 16 times 2 is 32, plus 18 more is 50. Okay, so I've got 50 oxygens over there. What times 2 gives me 50? 25. Right? That's the lowest balanced form of that chemical reaction. That is the chemical reaction that occurs in the engine of your vehicle. Okay, this stuff here is called octane. It is the active ingredient in gasoline. Right? So those are your 2 rules. Okay? First rule has to do with balancing in alphabetical order, and then there is the rule of 2. Start balancing with a 2. Okay, anybody need that? Okay. Next reaction type starts our replacement reactions. There's 2 types of replacement reactions, single replacement and double replacement. They work exactly like they sound. Somebody gets replaced in these chemical reactions. All right. So in a single replacement reaction, okay, and in any kind of replacement reaction, you are always dealing with ionic compounds. Replacement reactions only involve ionic compounds, never involve molecular, because they have to have charges swapping. There have to be metals and nonmetals, right? There can't be they can't be molecular compounds because they won't swap. Okay, so they'll react, and in this reaction, one of the ions in the compound is lost, and another replaces it. Okay, so it is very much like the situation in the picture there. Okay, we got like lonely dude here. Okay, and then this couple dancing. Lonely dude likes her. Takes buddy outside, rolls him, okay, takes off with the girl. Now we have a new lonely dude. Okay? Now, here's the thing about replacement reactions. Replacement reactions are very old-fashioned, meaning you will never have a metal replacing a non-metal, because then you would have 2 metals together. Okay? Which, in real life, that's fine. But But reactions are old-fashioned, and that doesn't happen. All right. First off, metals don't bond together chemically; it doesn't happen. Okay. And the non-metals, even though they do bond together chemically, it's not right in a reaction like this. Okay. So you always have to have a metal and a non-metal. So whatever you have by itself is replacing the thing like it. Okay. So in this case, there's a metal by itself; it's going to replace the metal that's already in this compound. Okay. If you had a non-metal out here, then it would be replacing the non-metal that's in that compound. Okay, is that making sense to everybody? All right. I don't know what's going on with my spacing here. All right, in this reaction here, we've got copper, which is a metal, okay, and reacting with silver nitrate. Okay, in that reaction, okay, the copper replaces the silver. Okay, so these two things here switch places, and we are left with solid silver, not a bad deal, okay, and copper 2 nitrate. Okay. Anybody see an issue with this reaction? Is copper multivalent? How did I know to use the 2+ charge for that compound? Well, no, I mean, what if I was predicting the products of this reaction? How would I know then to use the copper 2? How would I know that this is copper 2? The answer is you don't. Okay? The answer is you don't, because this isn't copper 2. This is copper, metal. It isn't an ion. It doesn't have a charge over here. Okay? How did I know to use copper 2 in this compound? Copper 2 is the most common charge. When you are not told, you go with the most common charge. How do you know which one's most common? It's listed first, right? Okay, whichever charge on a multivalent metal is listed first, that's the one you pick. Okay, that's going to come up in replacement reactions sometimes. You always go with the first charge. It is the most common. Okay, so this reaction does actually cause solid silver to plate out, okay, in the reaction. What I mean by plate out is if I put a piece of copper wire or a penny or something like that into a solution of silver nitrate over the course of several hours, okay, essentially like overnight, I would come back the next morning and find silver plated out onto what was previously copper. It would be in almost exactly the same form. Okay, they essentially perfectly replace each other. Right? You're never going to get rich with this reaction, so don't go thinking you can break into the lab and steal the silver nitrate. Okay? Silver nitrate, well, I suppose you could break into the lab and steal the silver nitrate, but if you're buying silver nitrate on your own, it's really expensive. Why? It has silver in it, and you can't get ahead on that reaction. Okay? All right. And then you have double replacement reactions. In a double replacement reaction, there isn't anybody alone to start with, nor is there anyone alone at the end. You have two couples, okay, and they switch. All right, everybody follow me there? All right, so the dance partners simply switch. And again, remember that reactions are old-fashioned, and we must end up with a metal and a non-metal to have ionic compounds on the other side. Okay, so in this reaction here, we got calcium chloride, aqueous, so dissolved in water, reacting with, okay, sodium carbonate, also dissolved in water. And you can see here that the metals have changed places with each other. All right, we end up, calcium is now with carbonate, sodium is now with chlorine. Okay, we have two new partnerships on the other side. Now, what happened in this reaction? What else happened in this reaction, I should say? Right, we formed a precipitate in this reaction. I started out with two things dissolved in water. They were both aqueous. But on this side, I have one that is a solid. Okay? And while in Science 10 you're never asked to write the states of matter on the compounds, you will be in Chem 20. Right? How would you figure out that one of those is a solid? Right, you just look at your chart. Right? You just have to check your reactions at the end. I don't know why they don't make you do that in Science 10. It's not that hard. Right? You just have to look and say, oh, in this one here, this one's solid. All right, that one's not soluble, so it's a precipitate. It's not hard. Okay. All right, balancing-wise. Okay, how many calcium over here? 1. How many over there? 1, so that's okay. Okay, chlorine, there's 2 here. How many over here? 2. Okay, 2 sodium here, 2 there, 1 carbonate, so that one's balanced. All right. And this reaction here, is actually one that you're going to do in your chemical reactions lab next week. Okay, you'll be mixing potassium iodide with lead nitrate. Okay, lead 2 nitrate, and what you get then is lead iodide, which is bright yellow. Okay. Okay, when you are communicating, writing a chemical reaction, that has to be balanced. So we've been talking about balancing all the way along, but just so that you see it. Okay. A reaction normally does not come with these numbers already in it. These are the numbers you add in order to make the reaction work. Okay. So, balanced reaction is one in which the total number of each kind of atom or ion in the reaction, okay, is equal to the total number that are in the products. Okay, whatever you start with, you have to end with, because you can't break the law of conservation of mass. Okay. We know obviously combustion reactions are special. They have 2 special rules for the balancing procedures. Okay, you balance them alphabetically. If you have an even number of carbons, you start with a 2. For every other reaction, there aren't really any rules. All right, the best way to generally start balancing a reaction is to look for something that is present in a large number and balance it first. Okay, so I would say in this case here, probably start. I don't know, you can start with nitrogen or you could start with oxygen. Oxygen's kind of a rotten one to start with though, because it usually throws things off. Okay, maybe let's look at hydrogen. There's 2 of it over here. Okay, so let's just say that this 3 and this 2 aren't here yet. Okay, I've got two hydrogens over here. Yes? Okay, so I need to put a 2 here to balance my hydrogens. Right? Now, that gives me how many nitrogens here? 2. Plus 1 more is 3. How many over here? 3. Okay, and over here I have 6 oxygens plus 1 is 7. 2 times 3 is 6 plus 1 is 7. This would be a tricky one because you have 2 things going in different places. All right, and so you have to remember it's the number on one side, not the number in this compound and that compound. Right? It's the total number of oxygens on both sides. Okay, so here's what I want you to do with these ones. All right, I want you to tell me what kind of reaction is occurring, and I want you to balance it. All right, just for right now, do the first 2. Okay, then we'll go over them, and then I'll let you do the rest, and then we'll go over them. So, what kind of reaction is the first one? Synthesis, right? We've got 2 elements reacting to form a compound. Okay, so this is a synthesis reaction. All right, I need to balance it. Now, I've got 3 hydrogens over here, and I only have 2 over here. What's the lowest common multiple of 2 and 3? 6. So what I do is I make sure that I have 6 on both sides, because that's the only way I'll make it balance. Right? So on this side, I would have to put a 2 here. 2 times 3 gives me 6. What do I have to put here? A 3, because 3 times 2 is 6. Now my hydrogens are balanced. I've got 2 nitrogens, and now I have 2 nitrogens. Always a good sign if one of the things you did balanced something else. Okay, as a result, always a good sign you've done something right. Okay, so that's what we do. We always look for the lowest common multiple if we have that kind of situation come up. All right, and oftentimes you're also going to be asked to write the equation in words, and this is why I told you earlier that it's so important for you to be able to name compounds correctly. Okay, what's this stuff? Nitrogen. It's just nitrogen. It's not dinitrogen. That's nitrogen in its element form. Remember, we went over which elements were the molecular elements, the special ones. Okay, nitrogen always comes as a pair. Oxygen always comes as a pair. Hydrogen always comes as a pair. Okay, so nitrogen plus hydrogen, okay, gives us nitrogen trihydride. Okay, and I'll tell you guys, every year, unit exam, I put questions like this on there, and I say, tell me what it is, write it out in words, and balance it. Okay, and each one be worth 3 marks. You're going to have a chemical reactions assignment, probably not next week, but the week after, where that's what you're going to do. Some of them will be write it out in words, some will be write it out in formulas, some will be predict the products, okay, and you'll have to do all of that stuff for them. Okay, number 2. Have you seen that one already? Yes. What kind of reaction is it? Single replacement. All right, so we usually just write SR, single replacement. Okay, I've got 1 copper over here and 1 over there, 1 silver, 1 silver, 1 nitrate. Is it okay for me to balance nitrate as a unit? Yeah, because it stays as a unit over here. Simplify. Don't try and balance nitrogen and oxygen separately in a case like that. There are 2 nitrates over here, though. That means I need to put a 2 here. How many silver does that give me now? 2. So I have to go back and put a 2 here. Okay, is it balanced now? Yeah. All right, try the other ones. Okay, I'll give you a few minutes and then we'll go through them together. Okay, so this one here written in words, copper, okay, plus silver nitrate. Okay, it gives silver plus copper 2 nitrate. Okay, so it looks like the combustion reaction is the one that's giving people trouble, and that's usually the way it is because combustion has all these special rules, right? We've got carbon and hydrogen plus oxygen giving us these 2 things. That's a combustion reaction. Okay, that's how you recognize a combustion reaction. It'll start out with carbon, hydrogen plus O2. Okay, so here's what we need to do first. All right, so first write combustion. Okay, how many carbons here? 1. All right, so I don't have to obey rule number 2 because rule number 2 only applies when there are an even number of carbons. All right, now I have to obey rule number 1, balance carbons first. There's 1 carbon, there's 1 carbon over here. So carbon's okay so far. All right, there are 4 hydrogens here. How many on this side? 2. So what needs to go here? A 2. All right, now I can look at my oxygens. 2 times 1 is 2, plus 2 more is 4. What times 2 will give me 4? 2. All right. The thing you cannot do, guys, when you're balancing reaction, I sometimes see people do this, is they'll change these little numbers. You can't do that. That's what you were given. You can't change what you were given. All right. And I know that sometimes, especially with combustion, the argument is, well, it's still oxygen. Well, no, it's not. Okay. O2 and O are different things. Right? One is chemically bonded to the other. Is oxygen special? Yes. It always comes as a pair when it's by itself. All right. To write this out in words, this is molecular. It would be carbon tetrahydride. Its common name is methane. It's fart gas. Okay. Okay. I would accept either on a test, but carbon tetrahydride is probably the best way to go. Okay. Plus oxygen. Okay, gives us water. And please, yeah, don't bother writing like dihydrogen oxide or hydrogen. Just write water. Everyone knows that's what it is. Okay. Plus carbon dioxide. Okay. Have you seen that reaction already? It was the example for which type? Simple decomposition, right? So we can write decomp, right? There's 2 hydrogens, 1 oxygen, 2 oxygens. That's not going to work. There's 2 over there. There need to be 2 over here. How many hydrogen are there now? 2. Oh, sorry, 4. 2 times 2 is 4. 2 times 2 is 4. Now we're balanced. Okay, write that out in words. Water goes to hydrogen plus oxygen. Okay. Is that making sense, guys? All right. How many people are done the last 3? All right. We may not get all of them done before the bell goes, but work on them. Okay. I'll give you another minute. Maybe we'll be able to get through one more here. All right. Let's have a look at these as many as we can here. I got, what kind of reaction going on here? I've got an element reacting with an ionic compound to produce an element in a different ionic compound. Single replacement. All right, so we would write SR there. Okay, balancing wise, 2 chlorine over here, but only 1 there. So what do I need to put here? 2. That gives me 2 sodiums. So I go back, I make sure I have 2 sodiums, there's 2 iodines, that one's done. Chlorine plus sodium iodide gives iodine and sodium chloride. Okay, we'll be working on more of that stuff tomorrow, guys. Have a good day.